everybody. Welcome back to Measure Theoretic Probability. When we last left off, we were talking about integrating with respect to a general measure, which could be a probability measure, but isn't for the moment. We're talking about general measures right now. So the setup is as usual. I had a non-empty set omega. I had a sigma field, or equivalently a sigma algebra, curly f on omega. And then we have a general measure mu taking values from curly f. So it takes in sets and it spits out non-negative real numbers. And when you look at omega and curly f together, you have a space that's ready for a measure. That's a measurable space. And when you look at the whole triple with omega included, you have a measure space. So we were looking at functions that take values in omega and spit out real numbers. And for what I'm about to do, I need a couple of things. I need f to be measurable. Now, f going from omega with curly f into the reals with the Borel sets, measurability means that inverse images of Borel sets are in curly f, inverse images under f. And for what we're about to do, I also need that f is simple, which means it's essentially a step function. I mean, it's actually a step function by definition with a finite number of step heights. But whether or not it looks like steps can get pretty weird because this omega is not even numeric and your sets may not be contiguous. And just give me a second, I'll get back to that. So yeah, I've got an f, omega to r. I'm going to assume it's measurable and simple. So if it's simple, let's assume that it has this form. A sum as I goes from 1 to n of little a sub I times indicator saying that omega is in a set capital A sub I. And in general, these little a sub I coefficients need to be real, but in everything we're going to talk about today, they are going to be non-negative as well, because we're going to be talking about only non-negative functions today. We're so close to pulling it all together, and that's going to be just a few minutes, just like it was in expectations, where we talked about simple functions and then non-negative functions. And then we pulled it all together in like 2 lines by saying that a general measurable function has a positive part and a negative part, and you can treat those as both non-negative and blah, blah, blah. So today, everything is still non-negative, so these coefficients would be non-negative. Now I'm going to draw an over-idealized version of this step function here, which looks like this for n equals 3. So n equals 3, that's pretty ideal. But what's really over-idealized is the fact that this is my omega axis, and I'm making it look like it's a real axis. It doesn't even need to be numerical. Remember when omega was consisting of coin toss outcomes like heads, heads, tails, and tails, heads, tails? So looking at it like this is just a way for us to visualize something for the moment, but this could look much more strange. And even though I've reduced us to looking at 3 different components, like a simple function with n equals 3, these sets could be wildly discontiguous. They don't have to look like nice tight intervals like they look here. So again, over-idealized picture. And we want to integrate this with respect to a measure. So last time we already started this, but the motivation is we're still going to measure area under the curve, but we're going to measure area differently. And for a simple function like this, we're talking about measuring some rectangles. Now, I'm not going to just measure the area of the rectangle differently. I'm still going to use length times width, or in this case, base times height. But let's look at the height. Let's look at the height. The heights here are little a1, little a2, little a3. These are real numbers, and this y-axis is a real axis. These are real numbers, and I can measure height in the reals with plain old Lebesgue measure. But the base lives in a strange set omega, and so I don't know how to measure the sort of widths of these bases. I'm going to use the measure mu of each of these sets. So we're still measuring area of a rectangle as a height times a base, and the height is still regular Lebesgue measure, but the base, the way we're measuring the base, has changed because the space that the bases live in have changed. Okay, so when you do that, we define the Lebesgue integral, or the integral of f over omega with respect to mu, for a simple function that looks like this. We just sum up all the areas of the rectangles, which come from the heights times those bases that have been measured differently. So this is going to be the sum as I goes from 1 to n of little ai times the mu measure of the set capital AI. This is all review, so I'm going a little fast. I'd also ask you to recall that if you want to integrate over some other set, presumably in curly f, but not the full omega, then you could think of that set as being, some part of this x-axis, and you need to pick out the parts of the rectangles that come from intersecting these sets with that set. So if you want to integrate f with respect to mu over a set A, For a simple function like this is defined to be the sum as I goes from 1 to n of little ai times the mu measure of capital AI intersected with capital A. And I'll review. So let's see. Also, last time we have talked about how to move from simple functions to non-negative functions. So suppose I have a measure space like this, and I have a measurable function from omega to r. If f is greater than or equal to 0, then we defined for any a in curly f, the integral over the set A of f with respect to mu to be a supremum of integrals over a with respect to mu of simple functions. And this supremum is taken over all possible simple functions that are trapped between 0 and f. And those are assumed to be measurable. If those simple functions are not made up of measurable sets, then none of this makes sense. So yeah, this is old stuff. And we noted last time that this original definition of an integral for a simple function that was on the previous slide, and then this supremum definition looked a lot like how we approached expectation when we were in a probability space and talking about a random variable x. In fact, in this notation, for a random variable x greater than or equal to 0, we now have that the expected value of x is the integral over omega of capital X dp, because what is a random variable but a measurable function? It's just the f in the probability space, and the mu is just capital P. So expectation as an integral, even though the random variable does not have to be continuous, and we are so far away from actually defining like probability density functions and the things you usually expect to see for expectations defined as integrals. So, and last time we went through a bunch of facts, so really quick recap, because I kind of want to continue my list right where I left off. We had a measure space. We had two functions, f and g, that were non-negative and assumed to be measurable. And we had sets a and b in curly f. Number one, if f was less than or equal to g, then if you integrate f with respect to mu over a, that is less than or equal to integrating g with respect to mu over a. Highly believable, highly intuitive stuff here, but we did prove it last time. And then this is like a monotonicity kind of result. And we had a second fact was another kind of monotonicity result. So if the set A was contained in the set B, then if you pick any one of these functions, say f, and integrate over a with respect to mu, that result is going to be less than or equal to what you would get integrating over b. And, for simple functions, this is really easy to visualize. You're grabbing a subset on that x-axis and you're grabbing a bigger subset. And if everything is non-negative, you're potentially grabbing more stuff, more parts of rectangles. So highly believable, and we proved it last time. The next thing we showed was for a non-negative constant c, you can pull c inside and outside of this so-called Lebesgue integral. Now, this certainly holds for any real c. It does not have to be greater than or equal to 0, but I do say that it's greater than or equal to 0 at this point because we do not know how to do this integral, this left integral, if the integrand is negative at this point. So yes, the fact that this constant is greater than or equal to 0, this will be relaxed eventually, but you can pull constants inside and outside of the Lebesgue integral. The fourth thing we showed, and the final thing from the last video, was if f of omega was 0 for all omega in a set A, then if you integrate f with respect to the measure mu over the set A, you will get 0. Again, highly believable stuff, especially if you think back to simple functions and measuring area. And if the base of your rectangles have area 0, then you're not accumulating anything. So your integral is going to end up being 0. So what is new for today? First up, actually fifth in this list that I'm continuing, is if the mu measure of a set A is 0, then the integral of f with respect to the mu measure over A must also be 0. To prove this, how do we work out an integral like this? We're going to have to look at simple functions trapped between 0 and f. I'm going to take any simple s between 0 and f, and I'm going to show that the integral with respect to mu over a of s is 0. And then we're done, ... Now, what is the ... I was a little lazy here. The definition of this integral right here is the supremum of all integrals like this when you run over all the simple s trapped between 0 and f. And if every one of those s integrates to 0 over a, then the supremum of a bunch of zeros is 0, and this integral is going to be 0. So we're done. So we just need to show this. Now, if S is simple, it has a particular form. I'm going to say the sum as I goes from 1 to n of little ai, and then I'm going to use capital AIs for the sets on the indicators. And the integral over a of S with respect to mu is, of course, the sum as I goes from 1 to n of little ai times the mu measure of capital AI intersected with capital A. Now, this set, capital AI intersected with capital A, is contained within capital A, and we do have monotonicity of measures. We did actually show this for a general measure, like way back, I think it was lesson 3 in this series. And so if this set is contained in the set A, then the mu measure of this set is less than or equal to the mu measure of A, but that is assumed to be 0 here. So what I can conclude right now is that the integral of this simple function is less than or equal to 0, but the integral of this simple function, because it's assumed to be non-negative, these coefficients are non-negative, and if you take the integral, you're going to get the coefficients times mu measures of things. Everything is non-negative. So this simple function cannot get negative. If we proved now that it's less than or equal to 0, that means it must equal 0, and we're done proving property 5 in the list. Okay, so one more in this list, and then I'll probably start another list just because the list is getting long, so I'll have back-to-back shorter lists. But this is one of my favorite properties in what we're doing right now, and that is that the integral of a function f with respect to mu over a set A, you can integrate over the entire space omega and then pull like an indicator function into the integrand. So this is an indicator that says that the omegas you're looking at are when they're in the set A, this indicator is 1, and the indicator is 0 otherwise. So to prove this, I'm going to divide this into 2 cases. In case 1, I'm going to assume that f is a simple function. And if so, I have to assume some form. So I'm going to assume the same form I've been using. The sum as I goes from 1 to n of little ai, and then capital AI sets for the indicators. Now, if we look at this function over here, I'm going to expand this out. The notation, I'm going to look at the indicators on A of omega times f of omega. This is just the indicator on A of omega times this. And I'm going to multiply the indicator. I'm going to bring it inside the sum. Now, when you multiply 2 indicators, you just get another indicator with the intersection of the 2 events being indicated. And so we get this. And this is another simple function. Good to note, if f was simple, then when you multiply by an indicator, you still have a simple function. You maybe messed up your sets a little bit, but that's okay. We do know how to do the integral of this thing. So let's do it. The integral over omega of the indicator times f with respect to mu is simply the sum as I goes from 1 to n of the coefficients, the little ai, times the mu measure of the sets used to define this product function. And those sets were the capital AIs intersected with capital A. So easy, right? Because this is a simple function. But this looks a lot like what you'd get if you were just integrating f to begin with over a. In fact, that's exactly what this is. And from here to here, that's what we wanted to show. So we're done with the proof in the case that f is simple. So let's move on to the slightly more complicated case where f is not necessarily simple. It is still greater than or equal to 0 for everything we're doing in here today. So to integrate f, I need to look at any simple s between 0 and f. I'm going to do that. And note that if I take this system of inequalities and multiply through by the indicator on the set A, this is still 0. The indicator is not negative, so nothing's going to flip. I end up with 0 less than or equal to the indicator on A times S less than or equal to the indicator on A times F. Now, if any of this is weirding you out, I would stop, take a moment, and look at both of these sets of inequalities with omegas inside, because these are really shorthand for saying this and this for all little omega in omega. And now I think it's pretty clear that if you have this, then you have this, right? Because any omega you plug in here, if it's in A, then this system of inequalities is identical to this. And if not, then this is just saying 0 less than or equal to 0, less than or equal to 0, but it does follow from this one up here. So if we have this, then we have this, but not necessarily the other way around. Okay, so let's integrate S with respect to mu over A. According to case 1 in this proof, because S is simple, we do know that you can integrate over the full omega and put the indicator over A in front of the integrand. So the indicator times S as the integrand. And then because of this inequality here, we know that this integral is less than or equal to the integral over omega of the indicator over A times F d mu. This is in fact property 1 in the list of things that we started last time that I recapped in today's video. So what I'm seeing here is I started with any simple s between 0 and f, and we just showed that the integral of s d mu is bounded above by this term. This is an upper bound on all integrals that look like this, running over all s that are simple and between 0 and f. So you know where I'm going with this. The integral over a of f d mu is defined to be a supremum, the least upper bound of all integrals like this, where you take the supremum over simple functions that are trapped between 0 and f. And what we had was an upper bound, and the supremum is the least upper bound. That least upper bound is less than or equal to any given upper bound. So we've got the integral over a of f d mu less than or equal to the integral over omega of this product with an indicator in there. Now, this to this, we wanted to show these are equal, and we have an inequality, so we are halfway there, and I want to show the reverse direction for this inequality. So let's look at integrating this. The integrand is the indicator times f, and how would I do this integral? F is not necessarily simple, so this whole thing is not necessarily simple, so I would have to consider any simple s trapped between 0 and this thing. So trapped between 0 and the indicator on a times f. Note that the indicator on a times f is always less than or equal to f because this indicator is 0 or 1. So this product here is 0 or f, and that's less than or equal to f. So the s that is trapped between 0 and the indicator times f also happens to be between 0 and f as well. And another thing we can get from this is that s vanishes off of a. What I mean by that is if you take s of omega for any omega not in a, you will get 0. So just, check that out over here. This is 0 in expanded notation, less than or equal to s of omega, less than or equal to the indicator on a of omega times f of omega. And if you plug in an omega that is not in a, that indicator is going to turn into 0. So you'll have your s of omega trapped between 0 and 0. And it's going to be forced to be 0 whenever the indicator turns off. And what this means, interestingly enough, is that s is equal to the indicator on a times s. I'm going to let you pause and think about that a little bit, because I think if I explain it, I'm just going to make it sound worse than it is, because it's not bad at all. I made that face because I almost said clear, and I hate to say clear, but I know I'm only going to make it sound hard, and it's not hard at all. So think about that. Convince yourself before moving on. Pause the video. Now let's move on. Okay, so as a final step, let's look at the integral of the simple s with respect to mu over the full omega. We just convinced ourselves that for the s in this problem, where we started with an s trapped between 0 and the indicator times f, that s is identically equal to the indicator on the set A times s. So I'm just going to replace s with the indicator times s. Now, this is a simple function, and so by case 1 that we've already proved in what we're trying to prove here, I do know that I can write this without the indicator and sort of suck that into the limits of integration, if you will. This is the same as integrating the simple function s with respect to mu over the full set A. But we did just see that s, assumed to be between 0 and the product thing, is also between 0 and f. And so by that monotonicity of the integral, this is less than or equal to the integral of f with respect to mu over a. In other words, by property 1 in the list of things we were proving today, or recapped today. So the final thing I care about is the integral over omega of the indicator times f d mu. This is a supremum of integrals over omega of s d mu, where s, the supremum, is taken over all simple s between 0 and the product of the indicator and f. And what we saw up here is that this is an upper bound for all such integrals. So the supremum, the least upper bound, is less than or equal to any given upper bound. This is less than or equal to the integral over a of f d mu. And this is what we wanted to show. This is the reverse inequality. So if you pull this all together and look back at the other slides, I know sometimes this is difficult not being in a classroom with several boards in front of you, but we have just finished proving that this is equal to this. In other words, if you want to integrate a function using the Lebesgue integral over a set A, you could integrate over the whole space and then pull that A into the integrand with an indicator. This is a super useful result. I use this all the time, and I think you're going to appreciate it once we get going here. Okay, I have an aside for you that's sort of totally out of nowhere and isn't going to appear to be leading anywhere for a bit, but I need to get this said before I get too deep into what I want to talk about today. And this is that if you have real numbers, little a sub ij, if they are non-negative for all I and j being 1, 2, 3 on up, then the double sum as I goes from 1 to infinity and j goes from 1 to infinity can be switched. When you think about switching double sums, if you do, and you've had enough analysis, you might think, oh, there's a monotone convergence theorem, a dominated convergence theorem, things like that. I actually am going to use this to prove those kinds of things coming up. I would call this a version of Fubini 1, Fubini's theorem part 1. Some people are going to say, oh, that's Fubini-Tonelli. Oh, that's just monotone convergence. Oh, Fubini has to do with inner product spaces and integrals. And, it just looks different all the time. But this to me is a version of Fubini's theorem part 1. So that's what I'm going to say. And that's all I'm going to say about it. I am going to prove this to you. I'm going to use it now without proof. But if you wait in this video until after my little outro at the end, I'll come back and do a quick proof of this. I just wanted to put that out there on the side because it's not measure theory, it's not probability, and I just kind of wanted to move on with some more results today. So stick around after the outro of this video if you want to see a proof of this. But, it's been like a whole 2 minutes without a list. I have 2 more things I want to put in a list. I'm going to call this more things. Number 1, I'm going to leave this for you to prove if you care, and that is if S1 and S2 are simple functions, the integral with respect to mu over any set A of the sum is the sum of the integrals. Totally straightforward. To do this, I would note that S1 plus S2 is still simple, and I would try to write down what that looks like. I would write down an expression for S1 using like coefficients A1 through AN, and for S2 using maybe B1 through BM, and using sets, and then figuring out how to combine all that stuff to write S1 plus S2 as its own simple function. And once you have it as a simple function, you know how to write this left-hand side down, assuming these things are non-negative. And you certainly know how to write the right-hand side down, and this is pretty easy to prove. So I'm going to leave this to you and go on to number 2 in my list of things here. If S is a non-negative simple function, I'm going to take any set A in curly F and define a function nu of A to be the Lebesgue integral with respect to mu of S over A. And you can imagine me choosing any A in F. And if you look at every single A in F and look at this expression, I claim that this is a measure on the space omega and curly F. I claim that this is a measure on the space omega and curly F. So let's prove it. So suppose that I have a simple function S that is non-negative, so it needs some expression. I'm going to write this a little different than usual because I need my N's and my A's for something else. So I'm going to call this a sum as I goes from 1 to M of little bi, and then indicators on sets capital B1 through capital BM. To show that we have a measure, there's usually an I and a double I, but there's a little bit more to being a measure that's usually hidden in the first line. And that is like, let mu be a non-negative function into the positive reals or something like that. So we do need this nu function of any set A in curly F to be, for example, greater than or equal to 0. And then we need the I and double I, which means that the measure of the empty set needs to be 0, and we need countable additivity. So for any A in curly F, nu of A is defined to be the integral over A of S d mu, and S is nice and simple, and we know how to write this down. This is a sum as I goes from 1 to M of little bi times the mu measure of capital BI intersected with capital A. This is greater than or equal to 0. That is easy to see because S was greater than or equal to 0, which means all of these BI coefficients are greater than or equal to 0, and mu being a measure is greater than or equal to 0. So this one is super easy. Nu of the empty set, this is defined to be the integral of S with respect to mu over the empty set. And we had this in our list today. I mean, this again probably falls into the obvious territory, but it was property 5 in our list today that said that if you're integrating over a set with measure 0, you do in fact get 0. So nu of the empty set is 0. So it remains for us to show countable additivity for this set function nu. For countable additivity, I want to take some sets, capital A1, capital A2, etc., disjoint out of curly f, and I want to consider the new measure of the countable union as n goes from 1 to infinity of the an. Now, by definition, this is the integral of s d mu over this countable union, and by definition, we're integrating a simple function. This is the sum as I goes from 1 to m of the little bi's times the mu measure of the capital Bi's intersected with this countable union. But you can rewrite the bi intersected with the countable union as the countable union of the bi intersected with the individual an's. So I'm going to do that. And note that these are disjoint in n as n moves. And now the simple function, I usually assume that the sets defining that are disjoint. I have that canonical representation, but that's not what I'm using here. I'm saying for the different n's, A1 is disjoint from A2, is disjoint from A3. And so in n, these sets, bi intersected with A1, bi intersected with A2, etc., are all disjoint. And this mu is a valid measure. And so I want to use countable additivity of mu right here to pull this countable union out of mu and turn it into a sum. So if you think about where we're going, we're trying to go to the sum as n goes from 1 to infinity of nu of an. And if you write that down and you can see that we're really, really close. I could pull this constant coefficient bi into the n, and I would be done if I could interchange the order of these sums. Two finite sums, fine. But with one of them being infinite, I do have to be a little bit concerned. So once I pull the bi in, you'll note that what I have here is a sum over I and n, so as opposed to I and j that I had before. And this is like a real number that I could call a sub in, if you will, lowercase a sub in. But here I'm going to use that aside that I talked about, Fubini 1, and say that, once we've proven that, we'll know that we can, in fact, because these are all non-negative things, interchange the order of the sum. Once you do that, note that the sum inside is exactly the integral of s with respect to mu over the set an, and that is exactly how we define nu of an, so we're done. The nu measure of the countable union is the sum of the individual nu measures. We have proven that nu is, in fact, a measure. Nu was defined by a Lebesgue integral of a simple function, so that's kind of cool. There's a lot more measures floating around here today than you thought. One thing to note is that if the simple s is Lebesgue integrable, so what does that mean? As a reminder, a simple function is always finite. There's a finite number of terms, and those coefficients, the little bi's, are always assumed to be finite. When you take the integral, then you get the sum of the coefficients times the mu measures of the sets. And the mu measures of the sets actually could be infinite. So even though you're summing only a finite number of things, a Lebesgue integral could be infinite for a finite sum like that, in which case you can still talk about this measure nu, but it just means that nu of the full omega is going to be infinite. But in the case where the simple s is Lebesgue integrable and this is finite, then nu of the full omega is finite. And so we do have that nu is a so-called finite measure. We talked about that way back again in lesson 3. The term finite measure just means that if you measure the whole space, you get something finite. I have a big, exciting theorem for you today that I won't get to prove today. We will prove it. And that is the Lebesgue monotone convergence theorem. This is going to look familiar, I think. So let me finish stating it, and then we'll talk about that. Suppose I have a measure space, an omega, a curly f, and a mu, and I have a sequence of functions, a little f1, little f2, etc., that I'm assuming to be measurable. I'm also going to assume that they are non-negative and increasing pointwise in omega. So 0 is less than or equal to f1 of omega, is less than or equal to f2 of omega, etc. For all little omegas in omega. I'm also going to assume that there's a limit for each omega. The limit as n goes to infinity of f at omega is some f of omega, which actually could be infinite. But there is some convergence here, as there should be, because these are increasing, so there's no oscillation. So it's going to increase to either some finite limit. It's going to increase to the supremum of these numbers in each omega, which could be infinity. But the punchline, I claim that number 1, this f is going to be a measurable function. And number 2, that limits can be pulled inside and outside of the Lebesgue integral here. So here I have a limit outside, and then I didn't write it that way, but this f is the limit as n goes to infinity of fn. So if I had written that in here, then you see the limit outside becoming the limit inside. So this is a super important thing. I'm sure you've used a version of this even outside of measure theory, and we will prove it in the next video. But I have some buildup, and I don't have that much time left. So one thing I want to point out is that I don't have anything under the integral sign. When you see that, you can usually, and for me for sure, but out there in the world, you could usually assume that this is an integral over the full omega. And this statement will in fact hold if I'm integrating over just some set A from the sigma field curly F. Okay, so we're going to prove this, and we kind of already did, in lesson or video 25, I believe, when the functions were random variables and the integrals were expectations. We had a theorem that looked like this. The random variables, the functions were actually simple in that case and not in this case. And we've done most of the work here. But it's at this point in the course that my approach at the beginning is going to come back and really bite me. And I knew it would. But I did it anyway. So I was very excited to get right into probability. If I were to have done this better, I have no regrets, but if I had done this better, then I would have talked about general measures for like 2 or 3 weeks worth of lectures at the very beginning, and then got to a probability measure, because if you know things about general measures, they're going to hold for a probability measure. That's just a special case, but going the other way, And so looks like we may have already proved this, but I do want to look more closely into this next time and try to prove this sort of from scratch and figure out how much we already know and what things we need to be careful about. So in my remaining time, I do want to talk about one thing I know we're going to need to be careful about when we prove this in the next video. And that is that if you look at the proof of the theorem I just reminded you of from lesson 25, one thing I used in there was continuity of probabilities. So we had continuity from below, which means if you have a sequence of sets AN increasing to a set A, the probability measures of the sets are increasing as a sequence of real numbers to the probability measure of A. And we had continuity from above. So if you have sets like A1 containing A2, containing A3, decreasing to what would be the intersection of those sets, then the probability measures are a sequence of numbers between 0 and 1 that are decreasing to the probability measure of A. We proved both of these things in lesson or video 9, I believe. And one thing we did was in the from above proof, I used the fact that the probability measure of A complement is 1 minus the probability measure of A to turn the argument around and turn the from above result into a from below result. So what do we have in a more general space? If you have a space, an omega, and you have an event or set A, then the mu measure of A, if you add it to the mu measure of the complement, that no longer adds up to 1. It adds up to the mu measure of the entire space. And that could be okay. We could kind of talk about a version of the complement. So we could say mu of A complement is not 1 minus, but the mu measure of the full omega minus the mu measure of A. And then I could repeat the exact proof from lesson 9. The problem occurs when the mu measure of the whole space is infinite and you can't get away with that. So continuity from above is going to have an extra requirement that the mu measure of the whole space be infinite, but I actually have a slightly weaker requirement that will work for us as well. So let me restate the continuity stuff for general measures. If I have a general measure space consisting of an omega, a curly F, and a measure mu, so continuity from below says that if you have a sequence of sets A1, A2, etc., increasing to a set A, I'll remind you of exactly what that means when we prove this, because I'll draw a picture. Then the mu measures of the sets are an increasing sequence of numbers increasing to the mu measure of A. And you have continuity from above. So if you have a sequence of sets A1 and then contained in that an A2 and contained in that an A3, and are decreasing to what would be in that case an intersection of the sets that you would call A, then the mu measures as the sequence of real numbers are decreasing to the mu measure of that set A if the mu measure of the whole space is finite, or a weaker condition is that you only need the mu measure of the A1 set in this in this sequence to be finite. So that's what I'm going to use in the proof. And that certainly would hold if the mu measure of the whole space is finite, but it doesn't, we don't need it. The mu measure of the whole space could be infinite here. Okay, so let's prove these. I'm going to even do a quick recap of continuity from below. Suppose I have a sequence of sets AN increasing to a set A. This means that A1 is contained in A2, is contained in A3, etc. And let me draw a picture here. They're increasing to the union of all of these. Hopefully this stops somewhere. I don't know. Could be getting bigger and bigger and bigger, but they're increasing to the union, and the union may end up being the full omega. Now, to use the fact that we have like lots of nice results for measures and disjoint sets, what we did then and what I'm going to do now is rewrite this. I'm going to define B1 to be this set A1. I'm going to define B2 to be everything in A2, but outside of A1. So we get a ring that's disjoint from A1. I'm going to define B3 to be everything that's in A3, but outside of A2. So that's the wider ring out here. And we are basically filling in all the same area here with disjoint sets. So what we have is disjoint sets, and the A set, which is the union as n goes from 1 to infinity of the original AN, is the same as the union as n goes from 1 to infinity of the Bn, but now it's a disjoint union. Furthermore, if you look at any particular A sub n, like A3 in this picture, you can build that up from A1, which is B1, and then the ring around that, which is B2, and then the ring around that, which is B3. In general, you can say that AN is the finite union of B1 through Bn. So we're almost done. The mu measure of A is the mu measure of the union as n goes from 1 to infinity of the AN. This is the same thing as the union as n goes from 1 to infinity of the Bn, but the Bn's are disjoint, so we can use countable additivity here of mu and get the sum as n goes from 1 to infinity of mu of B sub n. And then I can rewrite this as a limit, right? The definition of this infinite sum. This is a limit as m goes to infinity of the sum as n goes from 1 to m of the mu measure of Bm. And I can bring the sum back in with countable additivity, or really it's finite additivity, that's still countable additivity, to get the mu measure of the union as n goes from 1 to m of Bn. But remember, this is one way you can write am. So we're done. We have the mu measure of the union of all the A's written as the limit of the individual mu measures. And this, we're done proving continuity from below. This video is a little long, but I would love to get to something actually new. I did a lot of recapping, including this proof. By the way, I did say that the mu of the ANs is increasing. I had an arrow that was going northeast, and they're increasing by monotonicity of the measure because the A1 here is contained in A2, is contained in A3, etc. So the mu measure of A1 is less than or equal to the mu measure of A2, is less than or equal to the mu measure of A3. So in this limit, we do have, it's going through increasing values. Okay, so here's something new. The proof of 2, continuity from above. If the AN sets are going down to a set A and the mu measure of A1 is finite, then this means that A1 contains A2, contains A3. So we're getting smaller and we've got containment, and that sort of limiting set is what you get in the center when you kind of intersect them all. So let's draw another picture like this. The set A is some set down here. It doesn't have to be approaching an empty set. These rings could be like coming down to tighten up around this blue dot. But note that if you look at everything that's in A1, but outside of A2, you get this outer ring here. And if you look at everything that's in A1, but outside of A3, you get a wider ring. And the first ring was contained in this second wider ring. So what I'm trying to say here in general is that A1, if you subtract out A2, this is contained in A1 if you subtract out A3. And that's contained in A1 subtracting out A4, etc. And that this sequence, A1 subtracting out AN, as A runs from 2 on up, is increasing to A1 subtracting out A, which is going to be everything in this circle outside of that blue dot. So I've got the outer skinny ring and then a wider ring and then a wider ring, and it is approaching everything that's outside of A, but still in A1. So everything in A1 minus A. Okay, so note that A2 is contained in A1, and this means that the mu measure of A1 can be written as the mu measure of A2 plus the mu measure of everything that's in A1 but outside of A2. So the mu measure of everything that's in A1 but outside of A2 is the mu measure of A1 minus the mu measure of A2. And this only makes sense if the mu measure of A1 is finite. So that's kind of where I'm using that condition. Now, in general, the mu measure of A1 can be written as the mu measure of AN plus the mu measure of everything in A1 that's outside of AN. And by this, we have that the mu measure of A1 minus the mu measure of AN is the mu measure of A1 set minus AN. And so this is an increasing sequence in N. We saw that on the previous slide. A1 minus A2 is contained in A1 minus A3 is contained in blah, blah, blah. So using continuity from below, I can say that the mu measures of these sets are increasing to the mu measure of A1 with A subtracted out. But this is just mu of A1 minus mu of A. And so putting this left-hand side and this right-hand side together, the mu of A1 is fixed here in these two expressions. And we see that mu of AN is actually decreasing to mu of A. And that's what we wanted to show. So that was a little rush there, but I am out of time for today. Next time, we're going to look much more closely at Lebesgue's monotone convergence theorem. And I did promise that if you stick around after the outro, I would prove that Fubini won. So I hope to see you either after in a few minutes or in a few seconds or in the next one. So come back. Okay, so you're still here. That's pretty cool. I wanted to prove the aside that I used today when I proved that we could get a measure out of integrating a simple function. And I called it Fubini's theorem 1. And it said if you have real numbers, little a sub ij, greater than or equal to 0 for all I and j from 1 up to infinity, then the double sum over I and j can be switched. To prove this, I'm going to organize these numbers into a doubly infinite matrix. So my 1,1 entry is going to be A11, my 1,2 entry is going to be A12, etc. And I'm going to define a little notation. So the sum of everything in the ith row, I'm going to call this R sub I, R for row. And this is going to be the sum over j of the A sub ij. Similarly, I'm going to define the sum of everything in the jth column. I'm going to call this C sub j. And this is going to be the sum over I from 1 to infinity of Aij. And then I'm going to add up all the row sums. I'm going to call that R. So R is going to be the sum as I goes from 1 to infinity of the Ri. And given how I defined Ri, this is precisely the left-hand side of the equation we're looking at proving. And similarly, I'm going to define C to be the total of the column sums. And so if you just look at how I define the Cj, this is precisely the right-hand side of what we're looking at. Now I want to show these two are equal. And what I'm going to do is define something else and show that R is equal to this thing and C is equal to this thing, and therefore everything's equal. I'm going to call this other thing D. I don't know, I'm running out of letters. And I'm going to define it to be the supremum of the sum of the Aij's over like ordered pairs I and J. Taken from a set S, where S is any finite subset of the natural numbers crossed with themselves. So this doesn't have to be just nice, I goes from 1 to n and j goes from 1 to m. It could be just picking any sort of indices out of the natural numbers to sum over for each of those two sums. And as I said, we're going to show that R equals D and C equals D, and then we're done because then R would have to equal C. So for any positive integers, capital N and capital M, I'd like you to consider the sum as I goes from 1 to capital N of the sum as j goes from 1 to capital M of the Aij. This is the same thing as saying I'm just summing the Aij and I'm taking my i's and j's out of a set S, where S is defined to be the ordered pairs of i's and j's, where the i's run integer valued run between 1 and capital N and the j's between 1 and capital M. And this is going to be less than or equal to D, because D was defined to be a supremum of things like this over many more subsets of the natural numbers crossed with the natural numbers. So this is less than or equal to the supremum when you're looking at this over potentially other S sets. So I'm going to let M go to infinity. That means the sum in here is going to go to R sub I. And we're looking at the sum as I goes from 1 to capital N of R sub I as less than or equal to D. And now I'm going to let N go to infinity, and that is going to get us the full R on the left-hand side. There's no N on the right-hand side, so that's going to stay at D. And we get that R is less than or equal to D. Now our goal is to show that R equals D, and then we're done. And then you know what? Let's just say we've done it for columns as well, because it's very, very similar. So to show this, I'm going to let S be any finite subset of the natural numbers crossed with the natural numbers. And for any finite subset, no matter how weirdly defined, we can find integers capital N and capital M greater than or equal to 1, such that S is contained in all the ordered pairs you can get by taking I values between 1 and capital N and J between 1 and capital M. Just shoot those numbers up large enough to capture everything in whatever weird finite subset of N cross N you might have. Now, the sum over all pairs in S of the Aij, because these things are non-negative, if I sum over all of these things, which contain potentially more indices than we have in S, I'm going to get something bigger. And if I shoot like the M in this second sum here up to infinity, then because everything is non-negative as well, I'm using that here, I'm going to get something only potentially larger. And this is now the sum as I goes from 1 to capital N of the R sub I. And this is less than or equal to summing these up as I goes from 1 to infinity, which is what you would get if you wanted the entire R. So this is less than or equal to R. And this inequality from here to here is true for all subsets, finite subsets S of N cross N. And the supremum is taken over all of these kinds of subsets. And so I have an upper bound for this expression for every set S, every finite subset of N cross N. And this is going to be the supremum. The D was defined to be the least upper bound. And this implies that D is less than or equal to R. So we have that R equals D. And very similar argument will show that C equals D. And then we're done. If R equals D and C equals D, then R equals C. And we are finished proving this version of Fubini 1. So I am definitely out of time now. Thank you for sticking around. In the next video, we'll look at the Lebesgue dominated convergence theorem and a bunch of other things, hopefully. So please come back again. I hope to see you in the next one.